In this video, I'm going to look at chemical reactions, but in particular, I'm going to look at combustion reactions, both complete and incomplete combustion. So what exactly is combustion? When we use the term combustion, what we're really saying is something is going to be burning. Something is going to produce a fire and combust. So combustion is equivalent to burning. And anytime something burns, we're going to have two chemical reactants. There are going to be two things that are reacting as this material burns. One of the reactants has to be the actual thing burning, and that we refer to as the fuel. So we have to have a fuel. It's got to be one of the reactants. And typically in our world today, still at this late date, in modern times, fuels most of the time chemically are going to be hydrocarbons or something derived from a hydrocarbon. We rely a lot still on hydrocarbons, things derived from oil or fossil fuels, or things that we derive from there as we manipulate the oil. The second, other than the fuel, the second reactant is got to be oxygen. For something to burn, you need oxygen. If you can remove oxygen, you'll be able to put out the fire. The burning will stop. So if you think of fire safety, to put out a fire, you want to starve it of fuel, or you can starve it of oxygen, and it will have the same impact. But to get those two reactants to start to actually react with each other, to combust, to burn, you need something to ignite them. So you got to have a fuel, you got to have oxygen, but you have to have an igniter, and that igniter is going to be typically a flame or a spark. You can think of you going camping, and you could use a match to start the kindling burning, or on your stovetop at home, if you've got a gas stovetop, you probably have an electronic igniter, and it produces a spark and gets the gas and the oxygen to begin to burn. So now, what exactly do we mean by hydrocarbons? Here you see nice big fire burning. Most of the time we're utilizing hydrocarbons to burn. Typically, it could be coal. We still use a lot of coal in different areas. Coal is really just carbon. Other things might be mixed in with the coal, with the carbon, as we dig it out and excavate it from the earth. So other things would also end up burning when we burn the coal. Some of you are driving already, then obviously gasoline is a mixture of different hydrocarbons derived from oil. Gas stovetop, here you see a burner. Natural gas is actually a mixture of four different gases. Those are also hydrocarbons. Or something as simple as a candle. A candle, the wax itself is a hydrocarbon. So you can see there are a lot of circumstances where we rely heavily on the burning of hydrocarbons. Now combustions, they can be of two different classes. In the first class, we want to look at something called complete combustion. So if you have a fuel that undergoes complete combustion, what that means is we've got a hydrocarbon of fuel, and we've got sufficient, the key thing here is sufficient amount of oxygen to get the fuel to completely break down, to completely burn. If that's the case, if the fuel was a hydrocarbon and you have sufficient oxygen, you'll only get two products, and those will be carbon dioxide and water. Those are the hallmarks of complete combustion. Often, though, we're not after, obviously, the CO2 and the water. We're really after something else, and that's the heat from the combustion. It's combustion reactions are highly exothermic. We want to capture that heat and use it for something. So the derivation of energy is ultimately the real reason why we were utilizing combustion reaction. We would like to harness that energy, that heat, and get it to do something for us, to do some work for us. So when you hear exothermic, think of, in practical terms, we can do work. Well, what might that look like? Well, simple one, obviously. If you've got a gas stove top, we're going to use that heat to heat up food and cook our food. Or maybe we're burning that natural gas inside our furnace, and we're going to use that heat to heat up the air and warm up the interior of our homes. Or we might have a coal electrical plant where we're going to burn coal, capture the heat to spin a turbine and make electricity. Got a lot of electrical plants that are coal-based. There are a couple here in San Diego County. Or we could burn kerosene, for example, in this lamp, and not to use the heat probably, but to use the light to light up our camp. Or the gasoline inside an engine being mixed with oxygen and using that heat to move pistons and turn that heat ultimately into mechanical energy and move our car down the road. That is what we're after. That's the goal of conducting a combustion reaction. All right, so now how do you write a complete combustion chemical equation? Well, let's see what that involves. So let's look at a couple examples here. Let's say we take ethanol. We've run into ethanol before. We've used it in a couple labs this year. And you can see it's derived from hydrocarbons. It's a derivative. It's definitely flammable. So let's say we put some in a cup, drop a match into the cup, and it starts to burn. It ignites. And let's say we've mixed enough oxygen so it undergoes complete combustion. Well, what would the chemical reaction look like? Well, we know our two reactants have got to be the fuel, ethanol, C2H5OH, so it's on the left side. They didn't say mix with oxygen, but once they said that combustion was taking place, I knew that there had to be oxygen, and I remember oxygen is a diatomic molecule. So there's my two reactants, and once they signaled it was a complete combustion of a hydrocarbon, I knew I would only get two products, carbon dioxide and water. So here's the skeleton equation. Notice it does not look like it's balanced, but it is the correct equation for what's happening between this particular fuel, ethanol, and oxygen. On the other hand, another example, octane, one of the key components of gasoline, C8H18. Let's say inside the engine, we mix it with some oxygen, and it undergoes starts to burn, undergoes complete combustion. Let's say it's a really efficient engine. Again, I would want to write the chemical equation for that. So my two reactants are going to be the octane and oxygen, again being diatomic. And once they tipped me off that it was complete, I knew my only two products were going to be carbon dioxide and water. Again, this is the correct skeleton equation. I understand it's not balanced. We could always go back in there and we would want to balance that. All right, so that's one kind of combustion, complete combustion. You got to mix enough oxygen in with the fuel. If you think of the Bunsen burners we've used in lab a couple of times, there are little slots at the bottom, at the base of each burner that lets us control how much air mixes with the natural gas. That's how you can restrict or expand the amount of oxygen mixing with the gas. So if we have a nice blue flame, which would be an indicator of complete combustion, which is what we aim for, we have a good mixture. It's probably complete combustion. If we close those slits down, you're not going to get a very good mixture, and the flame will start to turn yellow. And when that happens, you get something called incomplete combustion. So again, we're having combustion, so you need a fuel, hydrocarbon, oxygen, and igniter. But the key difference here is you're restricting how much oxygen is going to mix with the fuel. And when that happens, you don't get complete breakdown, and you're going to get things beyond just carbon dioxide and water. You're going to get some intermediates. What those intermediates are, that's going to depend on what was the original fuel. How complex was it? The big thing, and the reason I'm even bringing up incomplete combustion, is one of the key byproducts now is going to be carbon monoxide. And carbon monoxide, you've heard a lot about this. It is a very dangerous gas, and it gets produced when a hydrocarbon undergoes incomplete combustion. It is incredibly poisonous. Hemoglobin in your blood is a big protein that carries oxygen and delivers it to all the cells in your body. And on that molecule where the oxygen binds is also the place where carbon monoxide can also bind. And if carbon monoxide bonds to the hemoglobin, it will block oxygen and therefore restrict how much oxygen is delivered to your cells. And it's really hard to displace the carbon monoxide, and it could ultimately lead to the death of an individual being exposed to carbon monoxide. So again, how would you recognize this? If you see a yellow flame, here's a burner on a stove, gas stove top, and it's not completely blue. I've got some red and yellow in there. That tells me probably the jets in this burner are dirty a little bit, and we're not getting a good mixture of air with the gas, and so we're getting incomplete combustion. Or these burners inside of a house furnace, again, isn't completely blue. You got some yellow and some red in there. Probably, again, the burners are a little bit dirty. This furnace needs to be cleaned so that we get a better mixture of oxygen with the fuel. And that's why in our homes we have carbon monoxide detectors trying to pick up its production. And this can happen. That's why you want to have your furnace inspected every year to make sure that those burners are burning blue and not yellow. Carbon monoxide, it's colorless, it's odorless, it's tasteless. You wouldn't know you were being poisoned. You will start to show symptoms, though, as the carbon monoxide bonds to your hemoglobin. You'll start to have a headache. You'll feel nauseous. You'll feel like you want to throw up. You'll feel dizzy, shortness of breath because you're not getting enough oxygen being delivered to your cells. As a result, you're going to start to feel lightheaded, and ultimately you could lose consciousness. You will faint. Ultimately, you would die from it if you're not removed from that environment pretty quickly. Here's a graphic that kind of illustrates that progression. A lot of people every year, 50,000 people in the U.S. go to the ER with symptoms of carbon monoxide poisoning, and in a given year, over 400 people in the U.S. will die from carbon monoxide poisoning, especially in the winter time like we're experiencing now. It can happen when you have a malfunctioning furnace. It can happen in a car even. If you've got a way for exhaust to get up into the passenger compartment, you could also experience carbon monoxide poisoning. Now, what would the chemical equations look like? Well, now they got to kind of tell us, they got to spell out what would be the products of the incomplete combustion, because there's no way of guessing that on your own. So here, for example, propane. So probably all of you have, like a grill at home outside on the patio. They use propane. Let's say it undergoes incomplete combustion, didn't get a good mixture of oxygen with the propane, and they're telling us an additional product is going to be carbon monoxide. So we've got two reactants, propane and the oxygen, obviously because it says it's burning. We got the CO2 and water, and then in addition, I'm also getting carbon monoxide. Anything that's more complex, so you can get all kinds of different products, and there's no way for you to know that ahead of time. If I were giving you a problem, I'd have to spell out what were the products. So got to be careful. Very practical reason for bringing up incomplete combustion. Carbon monoxide poisoning happens far too often.